Hey guys, and welcome back to another video on the channel. In today's video we're going to be applying Feynman's technique to this following integral here. So Feynman's technique pretty much makes the integral pretty much a parameter of another variable. So pretty much what we're going to do is pretty much make that a function of another variable. So we're going to let our function be let's say f of alpha, and we're going to place the alpha where that 6 is pretty much. So the reason we've done that is because since it's now in another variable, when we differentiate both sides, we're going to be able to pull the differential operator inside the integral and turn it into a partial derivative. Now a partial derivative allows us to treat the other variable as a constant. So for example, if we differentiate with respect to alpha, like we're doing here now, when we bring in this differential operator inside the integral in here, it'll turn into a partial derivative, which will treat the x's as constants pretty much. So let's just do that really quickly. And now what we can do is, once we've done that, is we can actually break this up into two separate bits. So for example, x to the alpha minus 1 over log of alpha can be rewritten as x to the alpha on log of x plus negative 1 on log of x. So let's just do that really quickly and break that up. So the reason why we've done that is because now if we're differentiating this entire thing here, that just turns to 0 because there's no alpha in that bit. So that will just cancel out to 0. When you differentiate this bit here, what we're going to do is pretty much, alright, if you're differentiating, let's say with respect to x of, let's say, 2 to the x, what you're going to get is 2 to the x log, natural log, of 2 in this case here. So for example, if we're differentiating up there, what we're going to get is when we differentiate x to the alpha, we're going to get natural log of x. So we've got the same thing here, that will turn to 0, and up here we'll have natural log of x. So it gives us this following expression, and we can see these natural logs will cancel out just to give us this following expression here. Now all we're going to do is integrate with respect to x, so we're going to add 1 to the power and divide by that new power, and that gives us that following expression there. Now what we're going to do is plug in our bounds. Now when we plug in 1, we're going to get 1 to the power of x plus 1 over alpha, to the power of alpha plus 1 all over alpha plus 1 minus 0. So we're going to have nothing there. So all we're going to have is this. Now this is a cool trick here. 1 to the power of anything is just 1. So our integral is pretty much just going to be this. 1 over alpha plus 1. So this is f dash of alpha. But we want to find f of alpha pretty much. So what we're going to do is integrate both sides with respect to alpha. So this side will turn into f of alpha again. And this will be turned into natural log of alpha plus 1 plus an arbitrary constant. So now that we've got this expression, we can equate this with our original expression, which is our integral. So now we have this is equivalent to this. Now we can't really solve anything at the moment because remember our original integral is when alpha is 6. But we got to get rid of this c somehow. So what we're going to do is let alpha equal 0. Now the reason why we're going to do this is because if you plug it into here, you're going to get x to the 0, which is 1, minus 1, which is 0. So that whole thing is gone. And then you're going to have natural log of 1, which is plus c. So in other words, c is going to be 0. So all we're left with is this following expression here. Now remember our integral was when alpha is equal to 6. So all we're going to do is plug in 6 back into our integral, and our integral is equal to natural log of 7 because 6 plus 1 is 7. And that's it. So that's our integral solved. If you enjoyed this video, give it a thumbs up and share with others.